So, we'll erase this and we'll start from scratch. So we have a ramp, and we have a box on that ramp. Hello, little box. And let's make this box 2 kilograms, maybe? No. Let's make it 10. So this is 10 kilograms. But now, the coefficient of friction will do, I guess, static. So if you were to solve for the coefficient of static friction in this problem, you would want to do your free body diagram, which I'll do it on the box, so I find that personally easier to do. So there's mg. Normal is in that direction, which that line probably isn't accurate to the scalar of the quantity, but it doesn't matter. And then there's a component of Fg acting in that direction, a component of Fg acting in that direction. And the force you want to take into account is whatever force is going to be opposing the part of the mg that's acting upon the x-axis. So if we were to do same type of calculations as we did last time. So it would be mg, we'll make this angle 45 again for simplicity, 45 degrees. Mg cosine 45, and we want the box to be in static equilibrium, so we're not going to have it move. So if you were to use the F net equals ma, but if there's no acceleration and it's not moving, then you can set F net equal to 0. So you can do mg cosine 45, which is working in the positive x direction, minus the frictional force, which is mu, as I told you, that is the coefficient of static friction, is what we're trying to find, minus the mu, the normal force. So we'll plug in mu normal. So in calculating the normal force, this is where it gets a little trickier. The normal force has to be balancing out the part of the gravitational force that is in the y direction. So you've got, as opposed to it being cosine 45, you now have the normal force being equal to mg sine 45. So we can plug that in, and you're going to have mg cosine 45 is equal to mu times mg sine 45. Now, I'm not going to go through all the extra work, but basically you have the setup there, and you're solving for the static friction constant. So that's the basic setup of any problem like that. The best advice I have for you is to use a free body diagram. It can be really helpful to visually see it. At least I'm a visual learner, and I enjoy seeing things visually. So, now that we've covered that, I guess we'll briefly talk about tension force. Tension force, we won't get into too much detail on the accelerated level, but it's basically if you have a box, you could have the tension force running parallel to the surface, perpendicular to the surface it's pulling, and that the tension force, if it was just like 45, it's going to be working in that direction at 45, versus if you had tension force kind of coming up this way, you would have to apply your trigonometry again and use the angle, stuff like that, but that's still tension force that's being applied. And then what we won't delve into, but what you probably will learn from another video, is if you have something like this, where there's like a whole system, sometimes you have to solve whole system problems. So the tension force would be used, so let's say there's a mass there, there's mass there, the tension is always working along the rope. So when you're solving for a whole system, you'd have to take into account the tension force. So, finally, the force we haven't really talked too much about yet would be spring force. So, for my purposes, we're just going to do spring force on a level plane. So if you had a spring attached to a wall right here, that's my little spring, so pretty, and we'll just say that its equilibrium position is, since we measure everything in meters, we'll make that 0.5 meters, because why not? So there's the equilibrium position. If you wanna, we're gonna attach a box to that, so there's a box at equilibrium. Now if we were to push that 0.25 in that direction, then you're going to have to start calculating the force of the spring. So the force of the spring would be equal to kx. So usually you can also see it's sometimes written as F of S equals negative kx. The only thing you want to be careful when you're doing these type of problems is you want to make sure your positive and negative directions are constant. So, for instance, if you were to make this the negative direction, then your force would be working in the positive direction. So that's when you would use positive kx. But then in doing that, your displacement, you would want to make sure is a positive displacement to account for the fact that a force is moving in that direction, as opposed to the reciprocal, which would work the opposite way. So if we push this 0.25 meters away from equilibrium, and well, we won't even give the constant of values just because we're talking through it. So if you're using F of S equals K, 0.25. So in some problems they could give you the F of S and say, can you solve for the constant? Or they'll give you the constant and the force and ask you to solve for the displacement and stuff like that. So it's never anything too tricky, but that's basically the breakdown of it. As long as you know that there aren't, if this box is resting on the ground, the only force that would be acting upon it is the spring force due to the displacement away from equilibrium. So, in concluding all of that, that's basically all forces you need to know. I guess we could run back through Newton's laws of motion one more time just to reinforce them. So Newton's first law, I'll write them up here. First law is inertia. Woo, big word. So inertia is the tendency for something to stay at rest, and that's basically the gist. It's only valid in non-accelerating inertia frames. The second law, which you will use all the time, F net equals ma. Yay! So much fun! And thirdly would be equal, and opposite forces. So Newton's laws have kind of set a basis for all of physics. When you're trying to make conclusions, you can use these to get basically anywhere in physics. So I think that concludes my physics talk. If you have any questions, let me know. Thanks for listening.